Hi, welcome back to Mr. Graham's Maths. Doing something new with this video, and I need to say a big thank you to D&D Resources who have given me permission to make some worked solutions using their resources. It is copyrighted material, so they have given me permission to be able to make these resources for you, and so I'm very, very grateful for them agreeing to that. So we're going to move through the PEAs in each of their workbooks. So that's practice external assessment. So this one is for practice external assessment number 1 for the complex numbers booklet. Now we're on to question 1 here. We have this surd, and we need to change it into a format that where the denominator has been rationalized. Now, if you have an updated calculator, the new versions of this, you can do that, but entirely on the calculator, and it will leave it in surd form. Unfortunately, my calculator that I have on my computer does not do that, so I'm going to do it longhand for you for this one. So we have the denominator here is 3 minus root 5. We need to times it by its conjugate. So we reverse the sign of the surd in there, and that will help us to get rid of the surd on the bottom. Okay, so now if we're timesing fractions, we're going to multiply across the top. So that will be like so, and multiply across the bottom. So 3 times 3 is 9. We have a minus 3 root 5, a plus 3 root 5, and then root 5 times root 5 is 5, and it's a negative 1 because we have a negative times by a positive. So this is 12 plus 4 root 5. And then we have that this bit cancels with that bit. And so that leaves us with 9 minus 5, which is 4. If we divide through by the 4, 12 divided by 4 is 3, and 4 divided by 4 is 1, so we have 3 plus root 5. Oh, and one other thing, for the next videos, I'm going to scan this at a bit higher quality to so these aren't quite so fuzzy. All right, but we'll just bear with me for now because this is the copy that I have at the moment. Right, so for part B, we have two things being multiplied together equals minus 6 over, minus 6 take away 8i. I've just written over the top of that just a little bit to make that really clear what that question is saying. Right, now you can expand that bracket and set it equal to minus 6 minus 8i, but that's a fairly long way of doing what is a basic achieved question. So instead think about it as being this bracket times this bracket. Two things times together make this thing. So if I wanted to work backwards, I would do a division. So a plus bi will be minus 6 minus 8i divided by 3 minus I. And that much you can do on your calculator. So we'll do a minus 6, take away 8i, and divide it through by 3 minus I. So therefore A is minus 1, B is minus 3 by matching up this side with this side. Okay, for part C, we're told one solution to this equation just here. Now, straight away, if you're told one solution, then the conjugate is also a solution. So 3 minus 2i is the second solution. Now, if we have two solutions, we can write that down the factors. So z take away 3 plus 2i is a factor. Z take away 3 minus 2i is a factor. And there will be a third factor that will equal 2z cubed minus 15z squared minus kz. I'm just going to go back and check the printout. I think that might not have picked up the printing properly. Just 1 second. Yeah, that's a plus kz. Just here, that's a plus. So let's pop that there as a plus, minus 39. Okay, now, just first of all, taking a look at the front term there so that we can figure out what goes in the front of this factor bracket. So to get that, we would do this z times the front of that factor, and it has to make 2z cubed, which means that this must be 2z. Then we look at the last piece, this minus 39. Well, that is made by doing this constant times this constant times this constant of the three factors. So 3 plus, or rather negative 3 plus 2i times negative 3 minus 2i times something, let's call it an a, has to equal negative 39. So if we do negative 3 plus 2i times negative 3 minus 2i, that's 13. So 13a is minus 39. So a must be, and remember a is the thing that we're working out in there, if we do 39 divided by 13, so a must be minus 3. So in place of that a, we can put in a negative 3, which means that our third solution comes from the factor 2z minus 3, set that equal to 0, so z is 3 over 2. Now we're not quite finished with this one. We have got the three solutions, but we also need to find the value of k that was up here in the original. We didn't need it yet to find those other solutions. We were able to use other pieces. You can do this at the start of the question if you like to do that first. That's fine as well. I'm doing it now at the end, but it really doesn't matter. There are a few ways to go about doing this. We could compare some coefficients similar to what we did in these earlier stages, but the safest thing to do is probably to use the solution that they've given us, the root of 3 plus 2i, and know that that makes this equation work. And so we substitute it in. So if we put in 3 plus 2i as the value of z, then this equation has to be true. So I'm just substituting in everywhere that there's a z, we're putting in a 3 plus 2i. That has to equal 0. And then what we'll do is go to our calculator and type those in. So I'll just pause while I type it in. It's going to take a little while. So what I've put into the calculator are all of the numerical parts of this equation. I haven't put in this k part here. So that gives me minus 132 minus 88i plus 3k plus 3ki has to equal 0. So easiest thing is to look at the real part here. That has to equal 0. So minus 132 plus 3k equals 0. So therefore, I'm just going to come over to the side a little bit here. So 3k has got to be equal to 132. So k must be 44. Now I just need to do a little remake of part D because the question has changed since the original video that I made, but we'll do this one. It's of a similar ilk anyway. So we have got to find the value of k that makes the argument of this thing be equal to pi by 4. Now this is a key sort of question that comes up where the argument is equal to pi by 4, and why that's useful is because pi by 4 is 45 degrees. If you make a triangle with the angle of 45 degrees, it's going to end up being isosceles. So you'll have, if you popped it on the Argand diagram, it would be over here in this quadrant with a positive angle of pi by 4, which makes this an isosceles triangle. Now that will become useful in a moment. Let's first of all start off by working out what's UW over V. So UW is 2 plus 8i times 1 plus ki all over 1 minus I. And what you might usually think to do is the multiplication on the top first, but I'm actually going to leave that to do it second because it has the k in it. So I'm going to do the division of 2 plus 8i over 1 minus I first, and then we'll times it by 1 plus ki. And I'm going to do that because I can do that on the calculator. So 2 plus 8i, oops, let's just fix that up. Oh gosh, here we go. And divide it by 1 minus I is going to give me minus 3 plus 5i times by 1 plus ki for the original bit on the top there. And now let's expand that and see what we get. So we've got minus 3 times 1, minus 3 times ki. We've got 5i times 1, and then 5ki squared. Now the I squared is the same as minus 1, so I'm going to change that to a minus 5k. Now if we tidy that up into the real and imaginary parts, we have minus 3 minus 5k plus 5 minus 3k. Oops, I added in a I there instead of a k. There we go. 5 minus 3k times I. Now we go back to what we were thinking about with the fact that this is an argument of pi by 4. It means that the real and the imaginary parts are equal. So minus 3 minus 5k has got to be the same length as 5 minus 3k. Now we do some rearranging. If I take the 5 over, minus 3 take away 5 is minus 8. And minus 3k plus 5 is going to be 2k, so k is minus 4. For part E, we have a bunch of algebra to work through. So let's start with u squared, where we'll get p squared plus 2 of this type, so p squared times I, and then plus p squared I squared. So the p squared I squared bit at the end, we can sort that out. So I squared becomes minus 1, so we end up with minus p squared. So those two cancel, and we've got 2p squared I. Now if we do u squared over v, that will be 2p squared I over p minus I. We rationalize the denominator like so. So we end up with 2p cubed I plus 2p squared I squared over p squared minus I squared. So this becomes 2p cubed I minus 2p squared, because the I squared turns into a minus 1. And p squared minus I squared will be p squared minus negative 1, so that's p squared plus 1. Now the modulus of u squared over v is to take this bit, and we want the real part of it first, which will be 2p cubed I over p squared plus 1. No, wait, that's the imaginary part. We'll take the real part first. In fact, I'm going to separate that before we go on and do this. Let's just move this out of the way. So this is super clear. The real part here is minus 2p squared over p squared plus 1, and the imaginary part is 2p cubed over p squared plus 1I. Okay, so back to doing modulus, which is to take the real part, square it, the imaginary part, square it, and then do the square root. So we end up with the square root of, actually I'm going to just change my color because I'm running out of space, or maybe not. We'll just do it down here. Okay, so if I square the top part, I will get 4p to the 4, p squared plus 1 squared. I'm going to leave it like that at the moment. I don't think we'll need to multiply it out fully. This one becomes 4p to the 6, p squared plus 1 all squared, square root that. Now the thing that gave me a clue not to need to expand that bottom bit is if we look back at the question, we're aiming for something that has p squared plus 1 on the bottom. So I'm hoping that will help us in our pursuits here. Okay, so if we then put that over a common denominator, then this is what we get just here. And then we can see we've got we can factorize out a 4p squared at the top here, and we would have p squared. Actually, we can take out more than just a p squared. We can take out a p to the 4. That's equal to just 1 plus p squared here, all over p squared plus 1 squared. So now you can see one of those can cancel with that. So we end up with the square root of 4p to the 4, which is, well, the square root of 4 is 2. The square root of p to the 4 is p squared. And then the square root of the bottom is p squared plus 1. And look at that. It matches. That's what we needed to show. All right, let's move on to question 2. So we're still in PEA assessment 1, but the second question. Okay, this one you can do by long division using the bus stop method, or you can do a bit of algebraic juggling, manipulation, whatever you want to call it. That second method is my preferred one, but I've got videos on both if you want to go and check them out. Okay, so first of all, looking at the fact that we have x plus 4 on the bottom, let's start with that and see how we could make this first term of x cubed. So we would need to multiply it by an x squared. Now if we do that, we will get the x cubed, but we will also get 4x squared. So take off the extra piece that we didn't want there of 4x squared, and then add the rest back in, 5x squared minus 2x minus 3. Okay, so we now end up with, let me just fix that up, x squared, x plus 4. If I bring that out to be on its own, minus, well, it's not going to be a minus, it's going to be a plus. So that'll be the minus 4x plus 5 makes an x squared. Like this. That's also over x plus 4. The reason I separated it so we can cancel that. So I've got the x squared out of it. Then we do the same with the next piece. So start with x plus 4. We need an x in front of it. That will make the x squared that we wanted just here. But it'll also add 4x. So we need to take off 4x. And then if we take off 4x and we also have the minus 2x that's up here, we'll end up with minus 6x. So I've done that step all together just to save us a bit of time and a bit of space in our working. So this will be x squared plus x, where the x plus 4 cancels with the x plus 4. Then we will add on the fraction with x plus 4. We will have x plus 4 on the top here to make the 6x that we want just here, or rather minus 6x. We need a minus 6 at the front here. The minus 6 will be timesed by the 4 as well, so we'll end up with negative 24. So we need to add 24, and then 3 will be taken off again. So plus 24, take off 3 is going to end up being a plus 21. So this equals x squared plus x minus 6, where we separate them out and we've got the x plus 4 cancels. Left over is 21 over x plus 4. So A is 21. For part B, we have, let me just get my pen here. We are multiplying together two complex numbers that are in polar form. So WZ, it helps these are already in polar form, because what happens is the modulus gets multiplied together, so k times k squared, and then we do cis, and the arguments get added together, like so. So this is equal to k cubed cis, and then if you're not confident with fractions, you can just put that into your calculator like this. So we are just adding it without the pi, just you put the fractions in themselves. That will come to 5/12, so this will be 5 pi by 12. Part C, we want the exact solutions from this equation that satisfy z cubed equals k, and k is a real number. So we'll start by finding the possible solutions to this and then check if they match this. Right, so first I'm going to multiply everything through by z so that we can sort of get rid of that z on the bottom and then rearrange it into a more normal looking quadratic. Oh, that was a +4 just there. Like this. Now if we solve that quadratic, you can use quadratic formula or completing the square. This one doesn't look like it's going to factorize, so my preference is completing the square. So when I've got things that are probably going towards imaginary numbers, I find completing the square a bit easier. So if we find half of 2, we pop that into our bracket just here, and we put it with the z, which came from the z squared. Now that would give us z squared plus 2z that we want. It would also give us an extra 1 at the end, where we get the 1 times 1. So take off that 1, then add the 4 back in. So what we have now is z plus 1 squared is equal to, well, minus 1 plus 4 would be 3. Take it over to the other side, and we get a -3. So z plus 1 is equal to plus or minus the square root of -3. So z is -1 plus or minus the square root of -3 will be to do √3i. Now let's test out those possible solutions in z cubed and see if we get k where k is a real number. So let's try out -1 plus √3i and cube it. I'm going to use the calculator for this. So -1 plus, and be really careful with your square roots here. I want to make sure that only the 3 is involved in the square root, and then it gets times by the I, and then we will put that to the power of 3. And if we cubed that thing, we get 8. Now I'll go back and check for the other solution. If we turn that into a minus, we also get 8. So both of those solutions work, and k equals 8. Okay, part D, we've got z is x plus iy. Prove that this can only be imaginary. So we have only one option here. We put x plus iy in for z, and we hope that it turns out to be only imaginary. So on the bottom of this fraction, we've got the conjugate. So instead we'll write x minus iy, and we're going to subtract the conjugate, x minus iy, over z. Okay, now we need to put that over a common denominator. The common denominator will be x minus iy, x plus iy. So from our first term, we need to do this numerator multiplied by this second term here to make it equivalent. So that happens to be the same thing. So it'll be x plus iy squared. Then we will subtract x minus iy. It was already over x plus iy, so we need to multiply it by the other part of the denominator. So this will be x minus iy squared again. Okay. Now, if we multiply out the top, that's going to give us x squared plus 2ixy plus I squared y squared minus x squared minus 2ixy plus I squared y squared. And on the bottom, we've got x squared minus ixy plus ixy minus I squared y squared. Okay, now we go through and do some cancelling. So let's take a look at that top line. If I take out that bracket, it's going to make that negative x squared plus there, and can I get this one, and a minus just there. Now you can see that the x squareds cancel off, like so. So does a plus 2ix. Oh, no, not that one. Whoops. The plus I squared y squared and the minus I squared y squared, plus this, these ixy terms on the bottom cancel each other out. So we're left with 4ixy on the top and x squared. Now this I squared just here is minus 1 times by minus, so it'll be a plus y squared, which we can rewrite that whole thing as being 4xy x squared plus y squared I. So therefore it's imaginary only. It doesn't have a real part to it. Okay, we have these complex numbers u and v, and we need to prove this thing. So let's start with the left-hand side. So if I add u plus v, that would be x plus a for the real parts and y plus b for the imaginary part. So then the modulus of u plus v squared would be to take the real part and square it, and then the imaginary part, just the coefficient of the imaginary part. We don't need the I. That's the definition of modulus. Now, if we're doing the modulus, we would square root that, but since we also are then about to square it, I don't need to bother, because that would get cancelled out. Okay, now u minus v. Actually, I'll write that just over the side here. So u minus v would be x minus a plus y minus b I. So then the modulus of u minus v squared will be x minus a squared y minus b squared. So let's put those two things together. U plus v, modulus of it squared, and then add together modulus of u minus v squared. So we will have x plus a squared, x minus a squared, y plus b squared, y minus b squared. Okay, next line, expanding those brackets, we get x squared plus 2ax plus a squared. Then x squared minus 2ax plus a squared, y squared plus 2by plus b squared, y squared minus 2by plus b squared. So we can see that the 2ax cancels and the 2by cancels. So we have x squared, a squared, two of them, in fact. 2y squared and 2b squared. Okay, now let's take the right-hand side. 2 modulus of u squared, 2 modulus of v squared. So that is 2 times the modulus of u is x squared plus y squared, plus 2 times the modulus of v squared, which is a squared plus b squared. And I don't need to do the square root because in the modulus part here, once it gets square rooted, it's about to be squared again. So I don't need the square root because it'll be square rooted away. So then obviously that is 2x squared, 2y squared, 2a squared, 2b squared, which is equal to the left-hand side that we found just up here. Those two things are equal, so we have proven the statement that we started with. Right, question 3. We're doing 4 over the complex conjugate of z. Well, z is equal to 2 minus 2i. So 4 over the conjugate of z, I'm actually going to do on the calculator straight away. So 4 divided by 2 plus 2i, and that is 1 minus I. And we plot it onto the Argand diagram, 1 minus I, just there. Okay, part B, we want to find the argument of u minus v, which is to do the argument of, well, 8 minus 2 is 6, and minus I minus 5 is minus 6i. Well, that makes an isosceles triangle. If we think about where it is on the Argand diagram, it's at 6 and 6. So that's 6 minus 6i just there. So therefore, the argument for that is minus pi by 4, because this would make a right-angled triangle. So that angle right there is 45 degrees, or pi by 4. And since it's under the x-axis, going around anti-clockwise, it's a negative. Okay, right. Bit of algebra to do again here. So we've got over root a plus root b. And to sort out the fact that there are those surds on the bottom, we'll multiply by the conjugate. So across the top, we have root a times root a b. So root a times root a would make a. So this is a root b. And then times it by negative root b, we will have negative b root a. And the bottom, we get a minus b if we multiply that out. And using that, when a equals 12 and b equals 8, we will then get 12 root 8 minus 8 root 12 all over 12 minus 8, which is equal to, well, the root 8 can become 2 root 2. So that's 12 times 2 would be 24 root 2. Minus, again with the 12 can become, we can take the 4 out of that. And if we take it out with the square root, it will become a 2. So we have a 16. And if we divided the 12 by 4, we've got a 3 left. And 12 minus 8 is 4. So 24 divided by 4 is 6. And 16 divided by 4 is 4. Okay, for D, we have z to the power of 4 is p squared I. So think about this on the Argand diagram. We are on the imaginary axis up here at p squared I. So we have z to the 4 is equal to p squared as a modulus, and the angle it's gone round just here is pi by 2. We need it in polar form so we can use de Moivre's to find roots. So the first root is to take the p squared and put it to the 4th root, and the argument gets divided by 4. So this equals p to the half cis, and then a half divided by 4 is 1/8, so pi by 8. Now we need 4 solutions because we have an equation to the power of 4. So the second solution, the easiest way I find to think about it is that when we've got solutions like this, they are evenly spaced around our Argand diagram. So if we've got the first solution was at pi by 8, then the next one will be a quarter of a circle around from there. So we would do, the modulus doesn't change, that's still p to the half, which is the square root of p, doesn't matter which way you write it. And our argument, the next argument along, will be to take the one we started at and add on 2 pi divided by 4. So a full circle divided into 4 pieces. That's basically what we're saying. So 1/8, add on 2 quarters or half, and we will have 5/8. So this is p to the half cis 5 pi by 8. So that got us this next one up here. The third solution we are looking for is just down here. And the fourth one will be here. So this is Z2, Z3, Z4. So Z3 will be to take the one that we just did and add on another half a pi, because that'll be 90 degrees, a quarter of a circle. So 5/8 plus another half will be 9/8. Now, since we've gone over the pi line like this, we should actually turn the argument around and do it as a negative. Most of the time you won't get marked incorrect, but if you are being complete about it, you would do 2 pi take away this. So 2 minus 9/8. Oops. There we go. It's going to be 7/8. So it'll be p to the half cis of negative 7 pi by 8 as its equivalent. Okay, last one. For this one, I'm going to go straight to the original one, this pi by 8, and I'll take off a half for that one because I know I'm going to need to come back down this way to go underneath. So let's go back to the original pi by 8 and we'll minus pi by 2. So 1/8 take off a half is minus 3 pi by 8, like so. Again, you could add on a half to the answer that we just got here to get the next one around and then work out what equivalent it would be as a negative. Okay, last part. We have that x minus p is a factor of this. So first of all, we can write down that if we put p into that equation, it will be equal to 0. Second bit of information we have is that, let me just get this color here, is this one here, that if we divide this bit by this bit, we will get a remainder of q. So that tells me that if I put negative p in, so a negative p squared minus b negative p minus c, we will get a remainder of q. And we're going to need to work a bit of magic to be able to use those two things simultaneously. So I'm going to start by saying this is ap squared, this is minus b times p minus c is equal to q. Now on this first equation, this gives me that p squared is equal to c minus pb, which means I can use that to substitute into here and turn this into a linear equation, so it won't have any powers in it. what I'm trying to get to is P equals something. So that'll help me put all of my things in terms where the P's are just P's and no P squareds. So if I replace P squared with C minus PB, then we can achieve that over here. So we have AC minus PB plus, I'm actually going to rewrite that BP so that it's the same as this one. Now, actually, this is a good example of where you try something out and it doesn't quite help you. So if you see now, if I do that, those are going to cancel. That doesn't help me to get anything in P. So I'm just going to go back a step instead of substituting in there and try something else. So if I take AP squared, bring the Q over here, it will be equal to BP, negative BP plus C, which you can see this piece is the same as this piece, just written in a slightly different order. So if those two things are the same, then P squared from this bit here is equal to AP squared minus Q from this bit here. Now those are the bits that I'm actually interested in turning out because that's what's in the given answer just here. All right, so P squared minus AP squared is equal to negative Q. Take out a factor of P squared and I get 1 minus A. So P squared is equal to negative Q over 1 minus A. Now that's going to be hard to square root, but again, looking back at the question, it gives me a bit of a clue. So instead of doing 1 minus A, if I reverse that, it's the same as the equivalent would be to make the top the negative of itself. So timesing the top by a negative 1 gives me the Q. So now P is equal to the square root of Q over A minus 1, which is what we wanted from the question. I'm sure there are other options of how you'd go about that, which way you'd rearrange it and everything as well. So if you did something else that was equivalent and came to the right answer, then you're fine.